Thanks for joining us. Today we'll walk you through how we partnered with Westinghouse's nuclear fuel team to transform their production planning and scheduling using a Simio-powered digital twin. We will share the key lessons and results from that journey. First, we'll provide an overview of the Westinghouse Electric Company and MOSIMTEC. For those not familiar with the nuclear fuel assembly, we'll provide an overview of the technology, the manufacturing process, and the components involved. For Westinghouse specifically, we'd like to discuss in more detail the complex global supply chain. Our client, Brad Parker, Director of Global Manufacturing and Material Planning, will comment about the planning process at Westinghouse, current and future vision. My colleague, Gerda Trollop, Senior Consultant with MOSIMTEC, will demonstrate some of the models and reports we generated. Finally, we want to share some lessons learned and best practices for similar implementations. Westinghouse is the world's leading supplier of safe, innovative nuclear technology. Founded in 1886 by George Westinghouse to prove the power of alternating current, the company has spent nearly 140 years redefining how the world generates and uses electricity. Their nuclear reactors are operating on multiple continents, with more installations approved in recent years. That same innovation drive now underpins the factory-built eVinci microreactor, which cleared a key US licensing milestone in March 2025. Through simultaneous progress on gigawatt-scale units, advanced fuels, and transportable microreactors, the company shows it can still push the frontier across every layer of nuclear technology. In this slide, we see Westinghouse's vision and values, which highlight the power of collaboration in advancing technology and services for a clean, carbon-free future. The central theme, together, emphasizes teamwork and unity in driving this vision forward. Key values include customer focus and innovation, speed and passion to win, and teamwork and accountability, which align with the company's goals of being at the forefront of technology advancement. At the bottom, the foundational principles of safety, quality, integrity, and trust reinforce Westinghouse's commitment to maintaining the highest ethical standards and operational excellence in everything they do. The company employs more than 11,000 people across 21 countries, underscoring its international reach. It operates with 5 distinct business units: long-term operations, outage and maintenance services, nuclear fuel, energy systems, and the innovative eVinci microreactor technologies. With over 90 facilities worldwide, Westinghouse's technology plays a pivotal role in generating nearly 50% of the world's nuclear power, emphasizing its critical role in the global energy landscape. Today, our focus is on the nuclear fuel business unit. Westinghouse is a complete fuel supplier, handling everything from development and manufacturing to core engineering, safety analysis, and fuel component manufacturing. Westinghouse offers 4 key fuel types. Pressurized water reactor is the most common type of nuclear reactor, using pressurized water as both a coolant and a heat exchanger. It is characterized by its safety features and reliability. In a boiling water reactor, or BWR, water is boiled directly within the reactor vessel to produce steam, which then drives the turbine. This design is simpler, but can be less efficient than PWR. Russia developed a type of PWR reactor, VVER, or water-water energetic reactor. This one operates similarly, but with differences in design, primarily in the pressure and temperature limits of the coolant. Finally, advanced gas reactor, or AGR, uses carbon dioxide as the coolant and graphite as the moderator, with the core being heated by nuclear fission. It offers higher thermal efficiency and is commonly used for experimental or future energy designs. Again, Westinghouse provides all components necessary for nuclear fuel, including development, manufacturing, and safety analysis, and have fuel manufacturing facilities located globally in the United States, United Kingdom, and Sweden. The corporate headquarters are located in Cranberry Township, Pennsylvania, with a global presence of customers. For today's discussion, as highlighted by the red circles, MOSIMTEC has been fortunate to collaborate with Westinghouse on Simio implementation projects across their key nuclear fuel and parts facilities. So where does MOSIMTEC fit in? We are a consulting services company focused on utilizing modeling and simulation technology to make informed decisions. With a 14+ year track record and consultants with even longer personal experience in applying modeling and simulation, We're fortunate to work across a broad spectrum of industries. Return clients include very well-known brands and others you may have never heard of, but serving a key part of everyday life. We have a saying, one day we might be flipping burgers for a quick service restaurant, and another you're working on rocket engines for space exploration. Our simulation work truly provides an opportunity to learn about a wide range of businesses, and more so, being able to guide our clients to know more about their own business continues to be really fulfilling. We're proud to call Westinghouse one of our many long-standing clients and appreciate the opportunity to share with you today some of the work we've done with them. I'm now going to play a brief video tour of the Columbia, South Carolina facility. Watch as uranium dioxide powder moves through each step of production, emerging as a zirconium alloy fuel assembly, ready for shipment to the customer.
At Westinghouse, what we do matters. We power the world and provide enough energy to meet 10% of the United States' electrical needs. Our nuclear fuel is produced here at the Columbia Fuel Fabrication Facility.
The product that we make here at Columbia, both the fuel and components, are shipped domestically to the United States to many customers all over the United States, and then also internationally.
The Columbia plant sits on more than 1,000 acres. Inside, the plant is divided into two main sections, the chemical side, where uranium is processed, and the mechanical side, where assemblies are fabricated. Enriched uranium is shipped to the chemical side of the plant. Here, it is converted into a gas and then into a powder. The uranium powder is tested to ensure it meets exacting specifications.
In the chem lab, we test the quality of the pellets and the powder as they come off the line, and we have to make sure that the quality is good enough for them to move on and put into rods.
The uranium powder is pressed into small pellets, each one about a half-inch long and holding as much energy as a ton of coal. Once pressed into shape, the pellets are fed into a high-temperature furnace that increases their density and converts them into a hard ceramic.
And then we grind them down to the proper diameter, and then we inspect it before it goes out to be loaded in the rods.
There are several production lines running at once, and control room operators monitor critical steps across the lines to ensure quality and safety.
Control room purpose is making sure all lines are running by each parameter that's set by engineers. So you have different parameters set for each line.
In the rod assembly area, pellets are loaded into tubes that are manufactured at a separate Westinghouse facility in Pennsylvania. The tubes are pressurized with helium and sealed, and the completed fuel rods move to the mechanical side of the plant.
Once it comes through the wall, it's now enclosed in a rod. It's encapsulated, and it's not just one pellet, but a series of pellets. And that rod, it gets treated. The ends get closed up, it gets polished, hardened on the tip.
Fuel rods are mounted into an assembly, the structure that holds the rods in place. A typical assembly can house 76,000 fuel pellets. Assemblies are manufactured on site using human skills and robotic technology. Once completed, assemblies are washed, inspected, and packed for shipping. At Westinghouse, what we do matters. We power the world.
The video you're about to watch highlights key components that make up a boiling water reactor, or BWR, fuel assembly. VWRs are just one of several types of nuclear fuel assemblies manufactured by Westinghouse. The video focuses on the major materials used in the top, middle, and bottom sections of the assembly. In both manufacturing and planning, we differentiate between nuclear and non-nuclear materials. Nuclear components include fuel rods, pellets, and their composite structures. Non-nuclear or mechanical components form the structural framework that supports the fuel rods. In the case of Westinghouse models, we concentrate on the manufacturing aspects within the facilities. The Simio model architecture identifies which materials are needed for a fuel assembly and triggers their production and consumption based on a detailed bill of materials. Each material type follows a specific manufacturing route, which allocates the necessary resources after consuming the required input materials. The model also considers inventory levels and work in progress before starting any production. To account for purchased materials, the model includes expected lead times for each item.
The planning process at Westinghouse, previously, we managed this through 5 separate sites, 5 different planning groups, all operating independently. The majority of it in Excel, with no integration, no constraint between. Manually entered spreadsheets, meaning that when we created the master schedule for 18 months to 2 years, what would happen then is if there was any scenarios or if there was a change, it would take us up to a week to be able to assess what that change was. And then each area would then flow down from that to allow it to be a final answer as could we do it or not. With the implementation of Simio, what we've been able to do is make these decisions a lot quicker. The simulation model can run and we can change parameters, as you know, in Simio, based off the tables, based off the demand data, and run a simulation to assess the impact. But not only that, it is an integrated schedule for all areas to allow us to make sure that we don't have gaps in our analysis. This has obviously vastly improved our ability to do what-if scenarios, to respond quicker to customer requests, unplanned outages, or any combination, to give the business a better forecast of where we have constraints, where we need to improve, or what the impacts will be to other customers. For example, should we decide that we need to prioritize this over customer X?
Thanks for that background, Brad. Curious if you mind commenting on your selection of Simio as the solution for Westinghouse.
The flexibility, the ability to add, take away. Other models that I looked at seemed to be more the structure of it, in terms it was almost like hard-coded, which made amendment difficult. You shall do it this way. Not, okay, we can be flexible enough to make it fit your process, not your process has to change to reflect our way of doing it. Adding to the scenario building with the complexity across 5 sites, to do that across 5 sites, and you'll see on the next slide how everything is integrated with a vertical supply chain. It could take up to a month for us to do a high-level change at the Columbia facility to assess the impact on the WZ facility, which is at the bottom of the vertical supply chain, which would mean that if WZ could not do it, we'd have to start all over again or do a partial assessment, which would not give us the full visibility of the impact of the change we are proposing.
This slide presents a high-level overview of the global Westinghouse supply chain, highlighting the interdependencies across various sites. Materials are produced at different locations and must be transported to the appropriate consumption sites to meet contractual commitments with both internal and external customers. These commitments are often tied to key performance indicators such as core loading plans, customer delivery dates, and/or contractual delivery dates. For most sites, Westinghouse utilizes Simio's planning and scheduling tools indicated by the green tick marks, while a few locations have been analyzed through independent project studies also utilizing Simio, such as the pelleting automation and eVinci projects. These models help ensure that each site can deliver components or fuel assemblies on time by generating detailed production schedules tailored to meet delivery requirements across the supply chain. At MOSIMTEC, we follow a proven process for deploying simulation models, a process we also use to implement digital twins at the Westinghouse sites. First, the functional requirements specification. We begin by developing a detailed specification document that outlines the system to be modeled, the modeling approach, and the required inputs and outputs. This ensures alignment on scope and expectations from the outset. Then, phased model development. Our modeling approach is iterative. We build the model in phases, enabling the customer to see a working end-to-end version early on in the process. With each iteration, more detail is added, allowing for flexible adjustments and informed decision-making throughout the development cycle. Verification. This is the formal process of testing the model to ensure it meets the specifications and it performs as intended. Verification confirms that the model behaves according to the design and logic outlined in the requirements. Data collection and ETL. Because we emphasize a strong specification phase, data requirements are clearly defined before development begins. This enables parallel workflows. Data collection and transformation can proceed alongside model construction, improving efficiency. Validation. Validation ensures the model accurately reflects the real-world system behavior. While verification checks internal logic, validation evaluates the model's outputs and assumptions holistically, confirming the full model ecosystem, the code, assumptions, and input data behaves like the actual system. Then analysis. Through model analysis, customers gain insights into system performance and behavior. This understanding typically deepens throughout the development and validation phases, enabling more informed decision. Integration and change management. At this stage, we help clients apply the model effectively to drive business improvements. For example, Westinghouse now uses its models regularly to inform production planning and scheduling. Ongoing analysis and support. In the final phase, customers continue to use the model for strategic, tactical, and operational decision-making. We provide formal training and model handoff and remain available to offer support or implement updates as needs evolve.
Thank you, Gerda. To roll out these digital twins at Westinghouse, we followed a milestone-based approach and roadmap. We couldn't wait for all data to be available or all systems to be updated. Otherwise, one will end up forever getting ready to be ready. Instead, we identified an initial milestone to make work with the data and information at hand. This effort provides a baseline functionality with standardized scheduling solution across plants and replacing or augmenting current spreadsheet planning outputs with Simio-generated outputs. More so, this effort truly identifies data gaps, capability gaps, and opportunities for automation. A subsequent milestone by site and in some cases at the corporate level was shared enterprise solutions, focus on eliminating manual data feeds and replacing them with automated workflows. One key benefit that came to light here was identifying a single source of truth for certain key data points, for instance, demand. If it's not captured and reported in SAP or SAP, it wouldn't get planned for. Where applicable, additional depth or breadth of the planned scheduling models were also addressed. Various sites at Westinghouse are at different levels of maturity with regards to milestone 3. This is where digital twin solutions serve strategic long-term planning, master planning, and even detailed planning. Each of these applications have a key prerequisite of either standardized source data towards a fully automated data pipeline or more granular near real-time data to represent accurate current state. This slide illustrates the flow of data across various systems that support capacity planning and scheduling in a manufacturing environment, in this case Westinghouse. Data originates from multiple sources. SAP provides key information about resources, materials, bill of materials or BOMs, routings, orders, and inventory. The MES contributes real-time data, including equipment status, work in progress, WIP, and current tasks. SAP Ariba handles data related to replenishment parameters, lead times, and reorder quantities. Excel may include labor qualifications, process data, and staff availability, amongst others. Not illustrated on this schematic is an ETL functionality, or extract, transform, and load, that move data from various sources into a central data warehouse or database. For Westinghouse, we fast-tracked an Excel Power Query-based approach as an interim solution for rapid discovery. This data feeds into Simio, which processes it to produce capacity feasible planning and scheduling. Specifically, Simio supports critical functions like master production scheduling, MPS, resource capacity planning, material requirements planning, and detailed planning. The output from Simio includes manufacturing orders, planned orders, inventory levels, task lists, resource assignments, and material requirements. This ensures that operations are aligned with the availability of resources and materials. This slide emphasizes the importance of data governance, ensuring the data is standardized, timely, and accurate. It also highlights the need for both static enterprise data to create the model and dynamic system data to initialize and operate the model. This data-driven approach follows a predictive and prescriptive methodology to forecast potential scenarios and guide optimal decision-making, ultimately ensuring plan adherence and improved operational efficiency.
For us, system understanding and definition begins with the development of a detailed functional design specification, as mentioned earlier. We believe that if you can't clearly describe a system, you can't model it effectively. This document outlines both the real-world system and the intended model, using diagrams and narrative to convey the necessary level of detail. The functional design specification is reviewed and approved by the client, ideally before model development begins. However, it remains a living document, evolving alongside the model as new insights emerge. Clients at the Vastra site have expressed that they find this document especially valuable as it provides a single, comprehensive reference that captures the entire process from start to finish. To build a true digital twin that extracts live data and runs a scheduling plan, it was crucial to ensure the right data came from the right sources at the right time. To prepare the data for import, we developed extract, transform, and load, or ETL, solutions to clean and integrate the raw data. This was an iterative process involving on-site stakeholders with many adjustments made along the way. Currently, the data import is Excel query-based, which is not the final enterprise version, but works well for the current stage due to its flexibility and quick implementation. Throughout model development, we made extensive use of error logs to provide feedback to the clients, helping them clean and standardize their data. The result of the ETL process is shown in this slide. It illustrates the model-ready data schema within Simio, highlighting the relationships between the various data tables. The models we created are fully data-driven, meaning they rely on real-time, dynamic data inputs. This approach provides users with the flexibility to quickly refresh and generate new plans that span multiple years. What previously took weeks can now be accomplished in just a few hours, enabling faster decision-making and more efficient planning processes. These are some of the key dashboards available after simulation run. For client confidentiality, the values have been desensitized and may appear as gibberish on the slide. These dashboards were instrumental during the verification and validation stages of the projects, providing insights into system behavior and performance. Production performance. After each run, users can see a comprehensive overview of production performance. This includes a comparison of the results from the generated plan to actual operational or contractual targets. This feature helps assess whether production goals are being met and highlights any discrepancies that needs to be addressed. The flow of materials. This dashboard visualizes the flow of materials throughout the production process, ensuring it matches the bill of materials. This is crucial for tracking material consumption and verifying that the right materials are being used at each stage of production. Throughput analysis. Detailed throughput data can be analyzed by area, providing a clear view of how materials and resources are performing across different parts of the facility. These reports are shared with area managers and planners to ensure coordination between departments, so everyone is aligned towards the same production plan. It also helps identify areas that may require adjustments to improve efficiency. Resource utilization. Resource utilization statistics are displayed, offering insights into how effectively resources, such as machines and labor, are being used. This data is key for identifying bottlenecks within the system, which could indicate areas where production is being slowed down. It also helps prioritize where capital expenditure should be applied, whether for equipment upgrades, additional resources, or process improvements. The resource Gantt chart. This is one of the most widely used dashboards at Westinghouse. It provides a high-level view of the system, displaying how sales orders, color-coded for easy identification, move through the various manufacturing processes within the facility. This chart helps track the status of each order and offers a visual representation of the entire production timeline, making it easier to identify potential delays or areas that require attention.
Implementing a digital twin can be challenging due to several common pitfalls. These include data issues like missing, incorrect, or poorly formatted information, which can undermine the model's accuracy. Our advice is to make sure you understand the source of the data and how it was measured. Stakeholder engagement is critical, as lack of buy-in or misaligned expectations can lead to delays or scope creep. Communication and transparency is key here. Make sure you engage your stakeholders from the beginning of the project and throughout, rather than presenting them with a solution at the end. Additionally, a deep understanding of the system is essential. We have a saying that if you cannot explain it, you cannot model it. This supports what Gerda shared related to the importance of functional specifications and process diagrams. You may have to coordinate with different subject matter experts across the organization to truly understand the system. Simulation projects have resulted in different departments sitting around the same conference table for the first time, understanding how their own area impacts another. Keep in mind current and future state of operations to correctly represent the system and possible model levers. Once you do start getting results from the model, be sure to be in a position to explain cause and effect of the different results observed. Lastly, model development can suffer from scope creep, time constraints, debugging complexities, or the use of the wrong tools, all of which can impact the success of the digital twin implementation. Have a strong project management add-on, yet allow for variability and adjustments in the project as needed. We are, after all, in the business of discovery and making sense of complex systems.
So for Westinghouse going forward, we have rolled out what I would consider the basic Simio simulation software. Now the future holds the opportunity to expand the utilization. We are focused on nuclear fuel. However, we are starting to see other parts of the business show interest. eVinci is one example. But how we document and future utilize this with the functionality we've not even touched on yet is where we will be trying to take the Westinghouse organization and the utilization of the Simio solution.
In closure, on behalf of MOSIMTEC, thank you to Westinghouse for the opportunity to closely work together over the last several years. Thank you for this opportunity to share a brief glimpse into the work we've done together. Finally, thank you to Simio for the opportunity to represent here at Simio Sync 2025. We welcome questions from the attendees, and where we are not able to address your question here, please reach out by email or find our contact details on the respective websites.